Okay, cool. Let's get started. So in going over test one, and sort of the big topics in test one, again, test one was all about these different integration techniques. So a lot of these problems were asking you to solve integrals and to show, sort of show your work in doing so. We have all of our integration techniques sort of off to the side in the back of our head. And as a reminder, those involved the first 5 techniques that are listed here. So besides all of our regular integration and just integration knowledge from Calculus 1, we were interested in sort of showing mastery of substitution, of integration by parts, of partial fraction decomposition. Those are, I would say, sort of like the 3 big techniques. And then there are 2 skills, skill 4 and skill 5, skill 3 and skill 4, that involved trig integrals, either using a trig substitution or other manipulation of trig functions. And so we'll see each of those at some point in the test. The first problem here was just a straight up question asking you to solve some integration technique, to solve some integrals using some sort of integration technique. Each of those, I think, could be solved using u substitution with an appropriate choice of u. And so in each of these, we had to figure out exactly what a good choice of u was. And so I'll briefly remind you that in u substitution, we were often choosing u to be some expression involving x's, and then we would compute du. Maybe I'll actually say u is some expression involving x's. Du would then be the derivative of that times dx. And we got there by remembering that du over dx is just another notation to write u prime. And so we get this substitution that would then allow us, if we wanted, to replace our dx with an appropriate expression involving du. And so one way that we could write this if we wanted to would be du over u prime equals dx. And there'd be a way there in which we could replace the dx with an appropriate expression involving du. But the overall goal was to identify and rewrite the integral in terms of these u's as opposed to in terms of these x's. And so in each of these cases, it meant that we were trying to figure out how to rewrite it in terms of, or how we were trying to choose a u so that everything could be nicely substituted in and out. And so what we got as a result, in each case, it involved a little bit of guess and check and trying to come up with a good choice of u. But the main criteria we had was that we wanted to choose an appropriate u so that the derivative of u was also present in the expression. We were kind of looking for the u prime dx to be sort of secretly lurking in the integral already. So in this case, in the first example, we could say, let u equal the square root of x. If we identified that, that would mean that du is the derivative of that. The derivative of the square root of x is 1/2 x to the negative 1/2. And so we could write du equals 1/2 x to the negative 1/2 dx. And after a bit of manipulation, we could end up seeing, let me see, we don't have a 1/2, but we could multiply that over. So then we could get 2 times du equals x to the negative 1/2 is just 1 over the square root of x dx. And we notice that 1 over the square root of x times dx is exactly this expression right here. So that entire thing is becoming our du. And then what we have up top, the e to the square root of x became our e to the u. So we made our choice of u in such a way that it sort of occupied the exponent of the e to the x, but the real reason we were choosing that is because when we went to calculate the du, we got that du would equal 1 over the square root of x dx, and we saw that in the expression. As I'm talking out loud, I realize I said this is a du, it should really be a 2 du. And so we could rewrite that as the integral of 2e to the u du, and we could proceed from there. The second problem is similar. We'd have to think a little bit about it, but we would realize that if we set u to equal the tangent function, then du is the derivative of tangent, which is secant squared times dx, and we would end up being able to find our du right here. And so that would become 1 over, not tangent cubed anymore, but 1 over u cubed du, and we would go from there. One thing I'll sort of say as we're talking here, a downside of lecturing in this way, just sort of using the whiteboard and lecturing over this test, is that as I scroll, this gets stuck here. So as a result, I'm going to need to erase what I'm writing as we go. Any questions about anything that we've written so far before I erase that?
How are you writing the integral with respect to du?
Oh, how am I writing the integral with respect to du?
Yeah, just can you finish the...
Yeah, let's finish one of the problems, 100%, 100%.
You don't have to go past the u part. I'm not fully seeing how you'd write the integral with the u in this one.
In A or B or both of them?
B, because you've written it for A.
Yes. Oh, okay. So I think I have it written just in a poor location. So
sorry, I see it.
writing it. Yeah. It's all good. It's all good. I will say one of the observations that I made here, sort of secretly, and I should have been more explicit when I mentioned it, is the integral, the secant squared over tangent cubed. One thing that I've sort of done in my head, but I didn't say out loud, is the secant squared, I just kind of left it up there. But in the denominator, I'm really thinking of this, the tangent cubed function, that's the tangent function cubed. So I have the tangent expression in the parentheses here, and that's what I'm cubing. And in that sense, sort of having the tangent in the parentheses is another strong signal that that it is a good choice of u. Similar to how up here, the square root was in the exponent. That was a sign that that could make a good choice of u. The fact that here it's that expression that's being cubed, that could make it a good choice of u as well. So there's that intermediate step, and then it just becomes a u cubed instead. Yeah, any other questions while we're here? Okay, cool. Let me go ahead and erase some of this. And we'll keep going. Okay, so as we go on, the next two problems, problem 3 and problem 4, are both integration techniques. Before we actually solve either of them, I want to point out how I'm thinking about approaching these. I guess they're both kind of similar in that they're integration problems, but they're both different in the structure of the integration expression itself, the integrand. What we have up top is we have a polynomial expression times a trig expression. And whenever I see a polynomial times a trig, or I see a polynomial times an exponential, one idea that I will often have in my head, I should maybe say polynomial times sine, polynomial times cosine, or polynomial times e to the x. One idea that I have in my head is to try to use integration by parts. I'll sort of say this as an idea, use integration by parts, and quote unquote shrink the polynomial. The idea here, as a reminder, integration by parts uses this this formula, and it's been a million years since we've thought about it, but the formula was as follows. It was, we're taking an integral of two things being multiplied together, and we can sort of stylistically write this. Well, first, let's just sort of straight up write it. We had a u. Yes, we had a u, and then we had another expression which was interpreted as a derivative, so v prime. Each of these are expressions involving x, and we're integrating dx. Stylistically, I like to write this as the integral of u, and then the v prime of x dx. I tend to write this as a dv. So all of that is becoming our dv. That's just notation to make the formula look a little simpler on paper. And the integration by parts formula said that this was equal to u times v minus the integral of v du, right? That was our ultraviolet voodoo formula that we had there, right? Ultraviolet voodoo, uv minus v du is a silly way to remember that. But what we have is a way in which we're converting an integral that we might struggle to know how to compute into a product of two functions minus another integral. And the hope is that the second integral is somehow easier to compute. That is the hope. So we can use that formula in this problem or in problems of the form polynomial times trig or polynomial times e to the x. And when I say we want to shrink the polynomial, what I mean is that we want to let the polynomial be the u expression. So as we sort of work through the formula, the polynomial, or the u, the polynomial, will be replaced down the road with a derivative of u, and it will get smaller, right? If it was previously an x squared, it will become a 2x. And the idea is we can use this to keep shrinking it, and in the end, we just can eliminate the polynomial and just integrate the trig or just integrate the e to the x. I should say the polynomial, I'm sorry, the trig or the e to the x expression is something that we need to be able to integrate in its own right, because if we're letting that play the role of the v prime, we'll need its antiderivative v in our final integral. But when we do this, what we realize, or I should say in this problem, if we attempt to do this, we can do so without much difficulty because the cosine of x expression can be integrated, and then the x squared expression, we can have the derivative of that. So in this particular problem, if we let u equal x squared, the polynomial expression, and our dv is equal to the cosine, what I always recommend is explicitly write out what du is. Du is 2x. I should really say du is 2x dx. I should say dv is cosine of x dx. And then our v, the antiderivative of cosine, is just equal to sine. So we identified our u, we identified our dv, we took the derivative of u, the antiderivative of v, and now we just plug into the formula, and what we get is the integral of u dv, so the integral of x squared cosine of x dx, equals u times v, so x squared sine of x, minus the integral of v times du, so minus the integral of sine of x times 2x dx. And you notice we have simplified the expression we're looking at. We started with a complicated looking integral. We were left with a slightly simpler integral, simpler because it's a 2x instead of an x squared, that's part of it. We're not actually done because we don't actually know what this is yet, but we could proceed and explicitly calculate this. And the idea here is that we would calculate this using integration by parts as well. So in maybe off here to the side in a slightly different color. Let's say the -2, let's keep the -2 out front, and then this was x times sine of x dx. In order to compute that, we would again need to use integration by parts. It's a polynomial times a trig. So we would let u equal the polynomial. We would let dv equal the trig. We would then let du, so we calculate the derivative of u, that just becomes 1 dx. The antiderivative of sine is minus cosine. As I'm writing this, I wonder if pink on gray was the best choice of pen color. Sorry about that. And what we end up here is we take that ends up equaling. So the original expression would be equal to, we have that -2 that's staying out front. But what we end up with then is going to be u times v. So x times negative cosine minus the integral of v du. And now we actually see why we have wanted to keep, minimizing this polynomial. The polynomial in that final integral has now disappeared, and we're just asked to find the antiderivative of negative cosine, which is negative sine. So we can end up calculating, we get this whole big expression, and then it's minus, the antiderivative there is a negative sine. And there's a million negative signs and parentheses, and hopefully I haven't made a silly mistake there, but we can end up taking that expression and plugging it back in for this expression. So we had to use integration by parts twice to end up with our final answer there. Now I guess the way the problem is worded, you'll notice, asks you to explain a little bit as well. So we'll notice that in the process of trying to solve this using integration by parts, we ended up with a -2x times sine of x. And the -2 doesn't really matter, so we had to calculate x times sine of x or the integral of x times sine of x as one of our steps. This can happen in these more complicated integration by parts problems where you integrate by parts, you get a new integral that you're trying to solve, and you have to wrestle with that new integral as well. And so this problem just explicitly asks you to work through that a little bit. I meant to compare problem 3 to problem 4. Problem 3 was a polynomial times a trig or a polynomial times an exponential. The one we have down here is a rational function. So this doesn't have any trig or any exponentials in it. It's really just a polynomial in the numerator divided by a polynomial in the denominator. And so when I see something like this, especially in the context of a Calc2 test kind of situation, I'm going to think that this is probably done using partial fractions. And the clue is that it is this rational expression, this polynomial divided by polynomial, right? In this case, just a constant polynomial divided by a quadratic polynomial. So as I'm looking at these different kinds of integrals and thinking about what technique I might want to use, this is sort of, I guess, a clue of using partial fractions. As far as the explicit calculation of this goes, I guess to briefly remind you how partial fractions work, our goal in partial fractions is to rewrite the denominator as a product. So we can think about this, let's rewrite that denominator. Instead of x squared plus 8x plus 12, we can factor it. And what is that going to be? That's going to be x plus 6 x plus 2. And so when we factor it, we're going to end up, our goal, I guess, in partial fractions is to try to, quote unquote, undo the common denominator. Let's try that again. Undo the common denominator. Right, and that's sort of where the name partial fractions come from. We have this combined fraction and we're trying to split it up back into its previous partial fractions. What that meant in this case was that we wanted to find a way to write it as a fraction of x over x plus 6 plus another fraction over x plus 2. And we had to use some algebraic tricks to solve for a and b. I'm happy to talk through that process, and if you would like to see it, shoot me a quick private message, and I'm happy to do it. But I would just say at this point, once we had the a over x plus 6 and the b over x plus 2, and we had figured out what an appropriate a and b were as far as values, a and b, we would end up getting that the original integral, right, the integral from 0 to 2 of all of that was just equal to the integral from 0 to 2 of a over x plus 6 plus the integral from 0 to 2 of b over x plus 2. And the trick then is that because a and b are just some constants, each of these is simpler to explicitly compute. We'd end up getting a times, because this is just an x to the first, and there's nothing extra going on there, we end up getting an a times the ln of x plus 6 plus a b times the ln of x plus 2. I am getting a couple of messages of people who want to see the A and B. I'm happy to do that very quickly. Before I do that, I just want to point out something. A common mistake I see in this kind of problem is trying to use the ln too early, right? So some mistakes or some some of you might get it in your head to take a look at this and to try to just jump directly to the fact of saying, oh, well, the 4 stays out front, and then we have a denominator, so that just becomes the ln of x squared plus 8x plus 12, right? Because it's a constant up front, and then there's this denominator, so, you know, we use an ln trick. Not true, not true. Easy mistake to make, right? As a reminder, the only time we can use an ln is if we have just a single x, so an x raised to the first power in that denominator. That would become the ln of x. And then through u substitution, if we have 1 over the integral of, let's say, mx plus b, let me actually just say x plus b to make that momentarily simpler. That just becomes ln of x plus b. But it's because that is a single a monomial, because it has just an x to the first in here, that we can use the ln trick. The x squared, not going to work, right? So we have to go through this partial fraction process. And when we do, we end up, again, let's talk through very briefly how to get the a and the b. So we're going to take this object down here, and we're going to multiply, I should say this equation, and we're going to multiply the entire equation by x plus 6 times x plus 2. And what that gives us, if we multiply the entire expression by that, we get a 4. That is not the right color choice. Let's go back to black. We end up getting a 4 on the left, right? Because the numerator, x plus 6 times x plus 2 cancel with those denominators. And then we get an a times x plus 2 plus a b times an x plus 6. And at this point, we end up with what we'll realize is a system of equations. So the 4 stays on the left, but over here, we can distribute the a and the b, so ax plus 2a. And on the b, we can distribute the b, so we get bx plus 6b. So we've distributed the a, we've distributed the b, and then we can regroup, not splitting it up into a's and b's, but splitting it up into x's and non-x's. So we can factor out an x, and we get a plus bx plus, and then our non-x's, we end up with 2a plus 6b. And all of that should equal 4, which is just a constant. So there is no expression of x on the left-hand side. We could actually write this if we wanted as 0x plus 4. That's another way that we can write the number 4. So this tells us that a plus b has to equal 0 because a plus bx equals 0x, and 2a plus 6b equals 4. So again, that's a plus bx equals 0x, and 2a plus 6b equals 4. And this is a system of equations. We've got our a and b are our unknowns. And so we can go on to manipulate this. And I think in doing so, we can solve for a and b. If we subtract the top equation from the bottom equation twice, we end up getting minus 2a minus 2b and minus 0. So we end up getting 4b equals 4. So b is going to equal 1, and then a is equal to -1. Right, that's for this specific problem, but in general, the argument here would be start with this equation. Whoops, still writing in white. Start with this big equation right here, manipulate it, or multiply both sides by the denominator x plus 6 times x plus 2 to get an expression like this. Turn it into a system of equations for a and b, and then try to solve that system of equations. In short, a whole bag of algebra tricks to figure out what a and b are. Okay, and hopefully that was coherent. Please, yeah, let me know what questions you have. Okay. So let's see. I'm not hearing any questions, so let's take a look and see what's next. Okay, the next two problems involve trig substitution and trig integral. So those were those final two techniques that we had talked about way back early at the beginning of the semester. The trig integral, or I'm sorry, the trig, let's just go in order. The trig substitution was a substitution problem that was kind of similar to a U substitution problem. It was a very specific instance of a U substitution problem. In a U substitution problem, as a reminder, we plugged in a U to equal an expression involving X. So we used a single letter U to represent an expression involving X. In trig substitution, we typically take a single value of X and use it to represent a whole other expression, typically a trig function involving theta. And if we do it correctly, we can actually simplify a denominator in an expression. Now, there are a few tricks in trig substitution, and this is the danger of coming into a review session a little bit cold. I did not review these, but I think we can figure these out. So there are sort of three common ones. Honestly, there are two common ones and one uncommon one. The ones that we focused on in class were if we had expressions of the form a squared minus x squared with a square root, the trig substitution that we often used was to let x equal a times the sine of theta. And then if we had an a squared plus x squared, we typically used the trick x equals a tangent of theta. And the reason for this was because if we used these particular substitutions and we set up an appropriate triangle to interpret it, we would find that these expressions appeared naturally. For the sake of completeness, this other one, which I care less about, so I don't think you have to sweat this one quite as much, is x squared minus a squared. So we flipped the order there. And this was x equals a times the secant of theta. Now, just to be really explicit about this, and to show you where these pop up and why these are natural, if I took x equals a sine theta, let's use that one as our example. So for x equals a sine theta, that would mean that x divided by a equals sine theta. And because of SOHCAHTOA, this is really like saying that if I had a right triangle with an angle theta, the sine of that angle, so the opposite over the hypotenuse, looks similar to x over a. And so I could write x is the opposite and a is the hypotenuse. If I then went to solve for that third side, the third side of the triangle would end up being, well, since a squared plus b, or since side length squared plus side length squared equals hypotenuse squared, I could solve for this side length and it ends up being the square root of a squared minus x squared. So you'll notice how this choice right here led naturally to a triangle that had this as a side length. And that's the idea behind trig substitution. It is a valuable, it is time well spent to take 15 minutes and maybe drink a cup of coffee sometime, and to think through how the other equations work similarly, using SOHCAHTOA and identifying the sides of a triangle. For the sake of this problem, or for the purposes of this problem, once we know this fact, and way back in Calc1 world, this might have felt like a long time ago, but we did know this fact, we could realize that with this substitution that we're trying to set up, this would end up being an integral that we could write of the form 9 minus x squared. And that's just 3 squared minus x squared. That would suggest that we use this substitution, x equals 3 sine theta. Then we would go on, we'd have a good time, we'd say x equals 3 sine theta is our substitution. And what follows is very, very similar to u substitution. We'd calculate a dx in this case. That would be 3 cosine theta d theta. And then we would substitute in. You'll notice in this case, the substitution is a little bit more straightforward in the sense that once I see an x, I can just replace it with 3 sine theta. And once I have a d theta, I can, once I have a dx, I can just replace that with the 3 cosine of theta d theta. But a lot of the joy of this comes from, at this point, we can begin manipulating that denominator using algebra and using the fact that sine squared plus cosine squared equals 1. And therefore, 1 minus sine squared equals cosine squared. So if we do some manipulation and we use these facts, we end up getting that that denominator simplifies down to the square root of 9 cosine squared of theta times 3 cosine theta. That just becomes 3 cosine theta over 3 cosine theta. And of course, those cancel, so this just becomes the integral of 1 d theta, which is literally just theta plus c. And as a final step, we might want to plug back in for theta. Theta, right, we had x equals a sine theta. That would mean that x over a equals sine theta, which we'd already written over here. But that just means that theta is equal to the inverse sine of x over a. So in this particular problem, we end up getting that our answer is the inverse sine of x over 3 plus c. And that often happens in these trig problems, right? We have a complicated looking integral involving a weird square root, potentially in the denominator. We use an appropriate trig substitution. Some magic happens, some nice things cancel, and we end up getting an integral that simplifies considerably if we're integrating with respect to theta. And then we translate back at the end. Yes, cool, cool, cool. Any questions or points of clarification about that? Okay. Okay, not getting anything. The final, I'll say this. I'm keeping an eye on the time. I'm happy to keep talking up until like the regular end of class time, like 9:15. We often end class at 9:05, but that's a artifact from when we had to sit in the same room and we couldn't be in the same room for more than an hour. So we're going nice and slow, which is great. I'm happy to keep talking for as much time as possible. Yeah, that's all I had to say about that. Problem 6. Problem 6 is a trig integral. Unlike a trig sub, our sort of topic of trig integrals just meant to use trig identities and be clever and cleverness to try to solve our integrals. So we needed a little bit of creativity and a little bit of cleverness to solve these. And it involved remembering a handful of our trig identities, which we learned back in pre-calculus and nobody really remembers them. We just sort of relearn them when we need them. The most important one for this lesson and in life, the most important one, is the same one from the previous page, the cosine squared plus sine squared, or let's say sine squared plus cosine squared, is always equal to 1. This is sort of the defining trig identity, the most important trig identity. It has the name of the Pythagorean identity. This is the same one, by the way, to try to draw different moments of the semester together. We just talked about polar coordinates as our more recent unit. We talked about polar coordinates, and this is the same identity that is helping us with the expression x squared plus y squared. I should really write y squared plus x squared equals r squared in polar coordinates. That's a total aside for test 1, but I just wanted to mention the Pythagorean identity is what was telling us that as well. And the idea there was that we had our translation where x was equal to r cosine theta, y is equal to r sine theta. And we see how x squared plus y squared secretly has a cosine squared plus sine squared in it. Okay, done with the aside. In the trig integral section, we used this identity along with some cleverness to rewrite expressions like this. And the observation we made here is that because the number 5 is odd, so we can rewrite 5 as 4 plus 1. And this means that the cosine to the 5th of x is really equal to cosine to the 4th of x times cosine of x. Our rules of exponents say that that's cosine to the 4th times cosine to the 1st. And our goal here, our sort of clever goal, was to recognize that we could peel off a single cosine and have it off to the side, while the other expression being even, we could rewrite this. So cosine to the 4th became cosine squared, and the cosine squared, we could use our trig identity, our Pythagorean identity, to rewrite that as 1 minus sine squared. So 1 minus sine squared quantity squared times cosine of x. Right, so the deal there, again, was that what we now have is an integral we're trying to compute, but instead of having that strange cosine to the 5th, we have a bunch of stuff involving sine times a single cosine. And so this is a moment that is ripe for U substitution from way, way back. Use U substitution, right? Bunch of stuff involving sine, and then there is a single derivative of sine, the cosine, times dx. So in this case, we could let u equal sine of x. We could let du equal cosine of x dx. And what we have is a bunch of stuff involving sine, so that's now a bunch of stuff involving u times a single du, and then we could proceed from there. All right. Any questions about that particular trick in this case? A lot of the sort of trig integral problems involved similar tricks. What we found is that even if we have an expression like, let's say we have an expression like cosine to the 6th of x times sine cubed, even if we had an expression like this, we could play a similar trick. The sine has an odd exponent, so I could rewrite this as sine squared, aka 1 minus cosine squared, times that lone copy of sine. And in this case, I have a bunch of cosine stuff. So cosine stuff, and then a single copy of sine, that would be my du in my u substitution. So even if I had cosine to the something times sine to the something, as long as one of those exponents was odd, I was good to go because I could use this trick. If both are even, we're in slightly more trouble. So if both of them were even, we might have to do some additional trig manipulation. And that was stuff that we talked about briefly, but is not something that I want you to stress about for the final. That was very, very specific. It would involve other trig identities like half angle or double angle identities and, nonsense like that. Okay. So at this point, we've actually solved a single problem, at least, from each of our big integration techniques and integration strategies from early Calc 2. And then what follows is a couple more qualitative questions, or questions that ask you to sort of explain your thought process or be, they are less direct plug and chug, a little more conceptual. Problem 10 asks you to describe a strategy you would use to find an antiderivative of that expression. We've already talked about this. This is a polynomial times an exponential. And so you would want to use integration by parts. The main thing that I was looking for in this problem was to identify integration by parts, to explain why, because it's, of the correct form. And then I was also looking for a few more words about specific strategy. In this case, making the observation that we want u to equal the polynomial term, dv to equal the exponential term, and the observation that you would need to repeat many times, right? Because if we use integration by parts once, this would end up being 99x to the 98 times e to the x as one of our expressions, and we would have to use integration by parts again and again and again, many, many times. Let me see, problem 8. Problem 8 is one of the trickier problems on test 1. It's very, very conceptual because we're asked to integrate a function that involves an unknown quantity w, which we literally don't have a formula for. So it really asks us to use our rules. So a really challenging one. It's very similar to the question we had on that particular skill quiz. And I believe this was integration by parts. Yeah, integration by parts. Yeah, let's get into it. So we had seen a problem like this before, though I think this was the most challenging of these kind of problems that we had seen to date. We're asked to compute a definite integral, and we're asked to compute a definite integral where w is a function in which we only know this list of stuff. So as far as a definite integral goes, the fundamental theorem of calculus says that a definite integral from a to b of some function will end up equaling the capital F of b minus capital F of a, where b and a are the two endpoints. So in many ways, our goal is to calculate an antiderivative of the expression in here, and then we want to plug in the endpoints appropriately. So let's give that a try. We notice that this is a 2x times an unknown expression, and so we might want to use integration by parts here. Let's give that a try. So using integration by parts, This is, again, of the form polynomial times unknown. So we might try to shrink the polynomial, and then we'll figure out how to deal with the unknown as we go. So integration by parts, we can let u equal to x. We can let dv equal the second derivative of w of 2x dx. Now du, the derivative of 2x, that's just 2. For v, we need the antiderivative of w prime of 2x. And here is where there's a potential wrinkle, this 2 in the expression. I'm going to claim that the antiderivative here is w prime of 2x divided by 2. All right, there is that extra challenge there. W prime of 2x divided by 2. Now the reason for that, just to be explicit and to say it, the reason for that is because there is secretly a u substitution happening as we calculate w, as we calculate v from dv. I'll just point out that the simplest way to see this is if we take the derivative of v, that's taking the derivative of w prime of 2x divided by 2. And then by the chain rule, that's going to equal w prime prime of 2x divided by 2 times the derivative of what's in the parentheses, so times 2. Okay, so according to integration by parts then, what we have here is we have our original expression becomes u times v, so that's 2x times w prime of 2x over 2 minus the integral of v du, so that's w prime of 2x over 2 times 2 dx. A bunch of the 2's can cancel. And then our final integral is itself a little bit challenging. So we have our w prime of 2x minus, and then the antiderivative of w prime is just w. But again, we have that additional now divided by 2 in taking that antiderivative. So our goal, right, we found this antiderivative, and now we want to plug in 0 and 1. And so we end up getting that this is equal to w prime of 2 times 1, so w prime of 2 minus w of 2 over 2. That's what we got when we plugged in x equals 1, and then minus w prime of 0 minus w of 0 over 2. And then we just have to plug in what those are based on the information up here. Okay, again, I think this was in many ways the most challenging problem on this first test. It involved some integration by parts, some u substitution, and also keeping in mind this additional information about w up at the top. So a really, really tough one. Keeping an eye on the time, we only have a few minutes left. I want to primarily focus on, we have 3 problems left. 2 of them are on improper integrals. 1 of them is on numerical approximation. I want to talk about the improper integral problem. And specifically, between problems 9 and 10, I want to talk about problem 10 as one that I saw a lot of people struggle with on the test itself. Problem 10 is tough because it doesn't actually look like an improper integral problem at first, right? It says to calculate the integral from -5 to 10 of 1 over x squared, and to do it carefully. And it's that carefully, I mean, we should always be careful, right? But the fact I tried to include the word carefully there to remind you that there is something sneaky happening here. Specifically, this function is undefined at x equals 0, and x equals 0 is smack in the middle of the interval from -5 to 10. Right, so our function 1 over x squared kind of looks like this. And I'm asking you to integrate from -5 up to 10 and to calculate all of that area. That's something that we can attempt to do, but not without improper integrals. And our strategy for doing this was we had to first identify the point where it's undefined. We then had to break this up into 2 different integrals from -5 to 0 and from 0 to 10. And then we had to calculate each of these integrals separately and then add them together. And the way that we calculate, let's take one of these integrals. Let's do the second one, I think. It doesn't actually matter, but let's go ahead and do the second one. Is we would have to calculate, because this is a problem at 0, we'd have to calculate a limit as a goes to 0 from the right-hand side, from the positive side, of the integral from a to 10 of 1 over x squared. Because if I take an a value, I can calculate this integral, no problem. I get an answer. It depends on a, and then I let a go to 0, and I see what I get. So then we have the limit as a goes to 0 of that. And when we calculate this, something interesting happens. The antiderivative of 1 over x squared is a -1 over x, right? Not ln of x squared, but -1 over x. Evaluated from a to 10. And so this becomes -1 over 10 minus a -1 over a, limit as a goes to 0. And so what we get in this case is that as a goes to 0, that denominator gets smaller and smaller and smaller. So this half of the integral gets bigger and bigger and bigger, and it actually blows up to infinity. So this side over here actually has infinite area, and our integral diverges. So when we try to carefully calculate this, we end up getting that the integral does not exist and that it diverges to infinity. So there's infinite area here. And we had to be careful because if we just plugged in 10 and -5, we would have gotten an answer that looked okay on paper, but was unfortunately incorrect. Okay, and that brings us up to about 9:15. I think that's a natural moment to stop. We were able to talk about every single skill except for numerical approximation, which I'm happy to talk about with you all down the road. Again, the idea behind a numerical approximation, I don't want you to have to memorize any formulas, nor do I want you to memorize any formulas. What I really want you to do there is to remember sort of the framework of how you set up a trapezoid rule, how you set up a midpoint rule, and which one might be an overestimate, which one might be an underestimate. My 30-second spiel on those integration techniques is that if you had a function that was concave up and you were using the trapezoid rule, you'd end up creating these trapezoids that went over the function itself, right? Let me highlight that a little better with a bigger trapezoid. We'd end up creating a trapezoid that went over the function itself. And so concave up led to a trapezoid overestimate. And similarly, if it was concave up, the midpoint rule would be an underestimate. Those rules would be flipped if it was concave down. And so the trapezoid rule and the midpoint rule kind of balance each other out in this interesting way, where one of them is often an overestimate and the other is often an underestimate. We can talk more about that on Friday or during office hours if anybody is interested. But otherwise, yeah, I'll see you all on Friday, where we'll talk about sort of the middle part of the material, the integration applications. If there's anything I can help you with in the meantime, please let me know. Otherwise, take care. Have a great rest of your Wednesday. And I'll see you all a little bit later.
Have a nice day.
Thanks, Audrey. You too.